5.4, analyzing graphs of polynomial functions. So this lesson's all about, like it says, we're going to analyze all different parts of a polynomial function. And most importantly, domain and range. We're finally going to talk about domain and range. Okay, let's get into it. So, graph each polynomial function by making a table of values. Now normally I'm a big fan of that, but in this case, it's a straight line. In this case, I don't want to plug in numbers to all that, it'll take 20 minutes. So instead we're going to use a calculator. So let me put in the new value. So I'm going to turn my calculator on. Then we go to y equals. I'm going to just type in that function. So 2x to the fourth. Remember, if you want to power that to bigger than squared, you can use the caret button. Lets you do any power you want. Kind of puts the square button to no use, actually. Type it all in. Plus x squared. And then minus 2x plus 4. I'm going to hit graph. And I guess it looks like that. So I can try to match it. So it looks like it crosses at 1 and okay. Where this is at 1, 2, 3, 4. It looks something like this. Not the best graph in the world. They wanted a table of values. You actually do that on your calculator also. Let's bring my calculator back up. If you notice the blue words, there's table right there. So second table. Then you go like this. Assume these are all the values. So like at 1 it does hit 0. You have 2, 3. Those are all your table values. So that's the way that works. That's why we're going to graph polynomial functions. Now let's talk about a couple of things before I move on. We're going to talk about how to find the zeros, or the x-intercepts, right? Also known as roots. Let's just say real zeros. In this case, that one's easy. It was at 1. We had 1, 0. If we look at just a graph, I have no idea where that one's at. Right? It looks like it's between 2 and 3. Now, if I bring back my table, look what happens between 2 and 3. See what happens there? It goes -4 to 34. It switches signs. So that's a good way to tell when there's a 0. Anytime you switch signs on a table, you know you had to cross 0 at some point. Right, the only way I could get from down here to up here is I had to cross the x-intercept, the x-axis at some point. So there has to be a 0 there. X-axis, whatever. So that's not an easy way to tell where there's a 0. If you don't have the actual value, you just look where there's a switch in the signs. And that's actually called the location principle. Right. So again, if you go from a negative to a positive, you have to cross the x-intercept, the x-axis at one point, and that's your 0. So without graphing, let's see if we can find the location of the zeros here. So negative, negative, positive. There's 1 right here. So there's 1 between -1 and 0. So that's 1, 0. And then, so when it's negative, positive, 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 negative. So there's 1 right here. Switch the signs again, right? From here to here, from here to here. It's supposed to be arrows. So between, now again, notice it's between the x values we're talking about. So between 1 and 2. Right, so where does it happen? It happens between 1 and 2. And then it goes, so again, positive, positive, negative, positive. It switches really quickly again. So there's 1 between 2 and 3. So this one has 3 zeros. Right, so really easy way to check is if you have a table, just look at the sign changes. And that's going to come up a lot, especially in calculus. You want to look at the sign changes. Those are your zeros. Okay, let's move on. Max and min points of a function. So, a couple of things. Some graphs have a max and a min. If you remember when we did parabolas, that was the max. There's no highest point, no higher point than that. If you're upside down parabola, that was a min. But I also want you to notice that this has no min, right? The one right here. it goes down forever, so there's no min in this case. And this one had no max. It went up forever. So if I give you a graph that kind of goes like this, there's no min or max. There's points we care about though. I care about this point right there. That looks like the highest point in the low area. Or I care about this point right here. That looks like the lowest point in the low area. So those points we call relative min or maxes. Because they're within the low area, it's the max and the min. So that's what we're going to focus on right here. Right there's a relative max, little hill. That's a relative min, low valley. There's no max or min in this graph because that graph goes on forever. But there is a relative min and relative max. So relative min, relative max. Also known as extrema. So if you actually for extrema, talking about the relative min, relative max. Sometimes they're also called local. Some books call them local min, local max. Same idea. So they're called extrema. They're also actually called turning points too. Right? So, because you see your graph turns, it's going down, then it turns and it starts increasing, then it turns, starts decreasing. So they're also known as turning points. And there's a special formula right here. The degree of the polynomial equals turning points plus 1. I should say the lowest degree of the polynomial. So look at the one right here. We have 2 turning points. So you go 2 plus 1, and I get 3. My lowest degree of this is x to the third. Which makes sense, right? Like that's an odd function. Starts on the bottom and switches, goes on top. The reason it's the lowest degree, not just degree, is because some graphs are kind of weird. Like if I give you x squared, that looks like this. But if I give you a power function x to the 4th, it also looks the exact same way. So I'm not sure about the imaginary numbers that come in. So we always say it's the lowest degree. That's what it is. It's the lowest degree possibly. It could be higher, but the lowest it could possibly be is x cubed in this case. So that's the form we're going to need to know. Lowest degree equals turning points plus 1. So keep that in mind. Okay, so in this problem, we're going to find a couple things, but it actually says right here, find domain and range. So let's talk about domain and range. I'm actually going to scroll to the bottom of my notes so I can add some stuff to it. There we go. Get there eventually. Here we go. I want to do some examples of domain and range, and we'll talk about what domain and range means on a graph. So domain, range. Let's do some examples real quick. It's like this. So that's good. Let's do a graph that looks like that. Blah blah. And let's do another one that kind of ends. So into that effect. And actually I'm going to throw one more in there. Okay, so those are my graphs. So if you remember what domain is, domain has to affect x values. So we're going to look at all the x values left to right the graph takes up. So this is the first one here. So find the domain of this one. So remember, domain is the x values. So what's the first left it goes? That goes at -2. The first right it goes is 1, 2, 3, 4. So my graph goes from -2 to 4. That's my domain, just -2 to 4. There's actually one more thing I had to add in. The way we write this, we're going to write this in interval notation. What that means is this. I want to know where we start and where we end. And there's a couple things that matter. If it's an open circle or an arrow, that means we can never reach it. So we use a parenthesis. If it's a closed circle, or like a dot, then it's a closed circle. That means we can reach it, so we use a bracket. So open circle is like a parenthesis, closed circle is like a bracket. So this is a line, so it's a bracket from -2 to 4. So those are the values you pick, and we're taking all the values from -2 to 4 my graph takes. That's just the value in between all that. And then the range is the same idea, but on the range we're using the y values. So we're gonna go low to high. So you have to go from small numbers to bigger numbers. That's the way it should go. So left to right, smaller to bigger, sending from the range, low to high. People are generally pretty good with the domain, but on the range they always want to go high to low. I don't know why. And high is spelled like that. There we go. So my lowest value, if you look at it, is right here, 2. The highest is 2, 3, 4, 5. So 2 to 5. And that's my range. So if you're looking at a graph, all the domain is the x values. What's the lowest, what's the highest? On all the ranges, is the y values? What's the lowest, what's the highest? So my range goes from -2 to 5, and my domain goes from -2 to 4. And that's the idea. So then we've been waiting for this whole time. Let's do a few more. So the domain on this one's gonna get a little interesting. So look at the domain. Farthest left I go, I see an arrow. Well, arrow means infinity, especially if we're going to the left. Actually means negative infinity. So first I go, it's just to keep on going. So negative infinity. First right is also an arrow, so positive infinity. So this goes from negative infinity to positive infinity. Notice the parentheses because you can never reach infinity, so we use the parentheses for that. The range, low to high. Lowest I see is -1. Positive 1. Highest I see is an arrow, so it's infinity. So my graph's gonna go from 1 to infinity. Bracket at 1, parenthesis at infinity. So 1 always infinity. Next one. Furthest left I see is right here, -4. Actually, look at its open circle, so parenthesis -4. And the first right I see is right here at 4. Bracket. By the way, this set, so let's talk about this for a little quick. This set in math, this is like a side, it's called a closed set. Close. There we go. It's because see how they're both closed things, so it's called a closed set. This set right here, see how they're both open? It's called an open set. And this one right here, it's closed and open, or open and closed, just to say. We call that a clopen set. Right? Closed and open. So that's where the name comes from. Anyway, let's do the range on this one. So you get another clopen set. So range lowest, I see right here is -2, open circle, open parenthesis. And the highest I go is 1, 2, 3. So there's that set. Again, another clopen set. Okay, last one of these before we get to that. We go back to what we're doing. Let's find domain and range of this one. Domain, farthest left, I see an arrow, so -infinity. Range, farthest right, I see an arrow again, so -infinity, positive infinity. Also known as all row numbers. So you small, you write the little all row number symbol. The range is low to high. So lowest I see is an arrow, so -infinity. And the range I see is also an arrow, positive infinity. Or row numbers. And that's going to happen. If it's an odd function, an odd degree function to say, it's always going to be negative infinity, positive in both directions. Because that's how the graphs roll. Okay. Let's go back to what we were doing. All the way up here. There we go. Now let's answer these questions. A. Estimate the x-coordinate of every turning point. Determine if those coordinates are relative max or relative min. So they want all the turning points. So there's one right here, one right there, and one right there. One, you can't see it, one right here. So again, they said estimate the x value. So let's say -2. It's an x, not lambda. X equals about 1. I should estimate. Oh, if you've never seen the symbol before, that means approximately. So when we're estimating, you always want to use that. And x equals, looks like 4. approximately 4. Now they want to know if it's relative min or max. Well, that's relative min. That's relative max. And a relative min. So that's that part. B, estimate the x-coordinate of every 0. So remember, we got that just knowing zeros are x-intercepts. So for B, just got to name all the x-intercepts. Again, we're just going to estimate. It looks like -3, -1, 2-ish, and 5-ish. So x equals -3. Again, we're estimating. 2 and 5. C, determine the smallest degree of the polynomial. So remember that for that one we knew the formula. Formula was degree, smallest degree, equals turning point plus 1. Well, we have 3 turning points. So C is going to be 3 plus 1, or 4. It's the fourth. It's an x to the fourth graph, at the very least. And look at it, makes sense. It's an even function, right? They both go up. Find a domain and range of the function. So the thing we just talked about. Okay, so let's do domain first. Domain, farthest left, negative infinity. I see an arrow. Farthest right, arrow again, positive infinity. Range, low to high. I actually have a lowest point, -75 looks like the lowest. Highest point, not this. That's a relative max, but there's actually higher over here. It's infinity, arrow. So another clopin set. -75 to infinity. And that's the domain range. A couple things. The domain for this chapter should always be all row numbers, negative infinity, positive infinity, because polynomial functions always have that domain. They never stop. So let's do another example to practice. Estimate the x-coordinates at every turning point. Oh, there's a lot. There's one here, one there, one there, one there. So for A, it looks like x equals, let's see, -1, 2, 3, 3, -2, -1. Again, really estimating. I actually haven't feel so bad I have to round it. So it's, oh, and then also at 1.5. Okay, this is an estimation. This is a min, max, min, max, min. Okay, that's A. The zeros, I only see 3. So about -2, about 0, and about 3. 1, 2, 3, yeah. 3.5, maybe. It's estimation. C, the smallest possible degree, remember, that's just turning points plus 1. I have 1, 2, 3, 4 turning points. So 4 plus 1 is 5. Smallest possible degree is 5. Again, it makes sense. It should look like an odd function. And it does. D, domain and range. Domain, farthest left, farthest right. We should actually know this already. It's all row numbers. Negative infinity to positive infinity. Every single time this chapter, right? It's never going to end. Now, this is an odd function. If you remember what I said earlier, that's not actually the exact same thing, because the lowest is an arrow, the tallest is an arrow. That's how odd functions roll. Right, so that's my domain and range. Let's look at one more, and so I'm not going to do the whole thing, because I think the first part of it's easy, but let's just look at the domain and range. Just to practice that a little bit more. So domain, farthest left arrow, farthest right arrow. Negative infinity, positive infinity. Range, you might say it's this, but arrows keep on going on forever. They don't show it, but they do. So if you see an arrow, that's always the winner. Negative infinity. Highest is right there, which is 1, 2, 3, 4. So negative infinity, again, low to high to 4. So that's my domain range for that one. Okay, let's move on. Oh, this is going to be fun. So in this one, sketch a graph polynomial function with the following characteristics. So it's, all they give us is this. So based on this, we have to try to draw a little sketch of what's happening. So let me try to give myself a little, something like that, I guess. Probably one down here also. Okay, that's not what I wanted it to do. I don't know why I did that. Okay, so look what they tell us. It's an even function, right? So you got to go. What does that tell me? Well, that tells me it either looks like this, right? They both go the same direction. That's what even tells me. My zeros, you got to remember, what's a 0? It's an x-intercept. So let me mark off some markings here. So I should have an x-intercept by -2. one at 1, at 3, and at 5. And now I know it's an even function, so it's your choice. You can start on top or bottom. I think most people like to start on top, so we'll start on top. Now all we're going to do is go through them all. So go through it, curve, go through it, curve, go through it, and go through it. And look at it. Looks like an even function, right? They both end the same way. And that's it for that one. Right? Just use what you know, fill it in. So send me the next one. So like that, I guess. No, okay. So in this one, they always make me mark it to lose it for some reason. Blah blah blah. So that'll be great, I know. A 5-degree function. So that right there tells me a couple of things. Right, 5 degrees. It means that it's an odd function. So it's like this. Right, or it can look the other way. You know, whatever you want. Some people might say, oh, you have to have 4 turning points. It's a 5th-degree function. Not necessarily. Remember, that's if you have 3 turning points, the lowest it could be is x to the 4th. Like, you can actually have lower turning points and still be a 5th degree. Other way around is where it is. If they tell you no turning points, that has to be lowest. Anyway, zeros are at -4, -1, so let's throw out -4. Remember, zeros are x-intercepts at -1 and at 3. And they give us one more thing this time. It's the max is at -2. So remember, the max looks like it's like that. So -2 should draw a max somewhere, probably up here. So we have that. Now in this case, I actually start from the max because I don't want to mess with my things. So I'm gonna start here. And just try to connect the rest, right? So go down through there. I'm gonna go through this one. I gotta connect through that one, and I get that. And look at it, does follow an odd function. If you wanted to try to get if you're trying to force the 5th degree, then you could always add like a little thing at the end, like a little thing at the end to make it 4 turning points. But again, you don't need to. You don't need to. So there's that one. Let's do one more. An even function with a minimum of x equals 3 and a positive linear coefficient. So this one doesn't give us that much out of it. So it's an even function, so we should know it looks like this, or it looks like this. Has a min at 3, so that 3 is a low min. And a positive linear coefficient. Remember what that means? That means you start on the top right. So it can't be this one, it has to be this one. Because the linear coefficient means you start on the top right. So that's all we have to go with. So here's 3, draw a min somewhere, doesn't matter where. And then just fill it out. It's on the top right. They don't tell me anything else, so there you go. That's one answer. Again, there could be more. You could have gone crazy with it. But that's the basics. Let's move on. Graph a function with table values, determine the consecutive integers, estimate the coordinates of the relative max and min. So again, let's look at one of these. I'm not gonna make you do table values. That's just pointless. I'll let you use a calculator and we just type it in and graph it. We do the same thing, like essentially we did at the beginning of this lesson. So x cubed plus 4x squared minus 5x. Just like that. Hit graph. Your graph looks like that. If I'm trying to find the zeros, again we can look at the table. So second table. You're looking for a sign change. Actually, we already got 2 zeros. Or you can look for a 0. Remember, if they give you a 0, that's a 0. So I have it at 0 and 1. I should draw on the graph of it. It's something like this. I forget. And that's actually, it can't be because it's x cubed. Oh, I'm a failure. Must have been, I'm just gonna look at it. Okay, so like this. Some side effect. My zeros were 0 and 1. For sure. Right, because again, look at the graph. Look at the table. Happen at 0 and at 1, those are just zeros. And then it wants me to find the remaining 0. So again, you look for a sign change. So keep on going. Oh, well, I actually got a 0 again. -5. So those are my zeros. Do you want me to estimate the relative min and max? Well, we have a calculator. So if you want to find the min and max with the calculator, all you have to do is second calculate and go to min or max. I'm not sure if we did this before, but we do it the exact same way as finding 0. So let's say we do the min first. So min is right here, right? So I like to go to the min, then go low left bound, go back to the min, go a little right of it. Gives it a nice little area to check for the min. Hit enter. My min's at 0.5 and negative 1.3. Estimate the x coordinate, so I just need the x coordinate of the min. It was relative min, I should say. 0.57. And then relative max. So relative max happens, I can't really see it, but that doesn't matter. I could fix my graph if I want, my window. But really, I know where it's at. I just gotta go close to it. So it's up here somewhere. Just gotta go left until I see it. Come on. There you go. So right, that's left of the max. Then move it right. Come on, go in. See, now it's on this side, right? So that's definitely left and right of the max. So hit enter. And I get negative 3.18. Again, it's one of the x value. It's my relative max. So there we go. That's how you use a calculator to find the relative min, relative max, find the zeros that you want. You can also just find the actual zeros in your calculator. But anyway, that's the idea. Let's get past that. The same thing. This is just what we just did. Find the relative maximum using a calculator. Showed you that already. Let's go to an application problem. So let's look at this problem. I like these. The deflection d of a 10-foot long diving board can be calculated using the function this, where x is the distance from the diving board. Again, super important. X is this between the diver and the stationary end of the board and the feet. So they're saying, like, if x is 2, that means you're 2 feet away from this box right here. That'd be x, right? So that's all it's saying. How far are you from the base of it? Make a table of values for the function 0 to 10. So again, I'm not going to make you make a table of values. We could use a calculator. It's the same thing, because if you made a table of values, you can be plugging into your calculator anyway. So 0.15 x squared minus 0.0005 x cubed. So I get that. Now they only want it between 0 and 10, so that I am going to do that. I'm going to fix my window there. That's going to affect me. Fix the window. So my x min and my x max. X min should be 0. X max should be 10. So it does affect my graph somewhat. Let's go to window before I graph it. I want that to be 0 and 10. I don't know about the y, they didn't give me any information, so let's see how the graph goes. So I can something like that. So graph the function. Looks like this. If I really want the table again, I could find it. There's a table. Scroll up. Whoops. Scroll down. Get the values you want. Come on, come on, come on. Right, there you go. I mean, at 10, it's like 11.3. What does the end behavior graph suggest as x increases? Well, let's look at it, right? So here's x. Here is the distance of the board, right? How, like, again, distance is how, like, floppy it gets. Well, it looks, based on the graph, as x increases, the floppiness is an increase. That it will, end behavior suggest, what does the end behavior of the graph suggest about as x increases? That d will increase. That d will increase. Okay, will this trend continue indefinitely? Anytime they ask you this question, 99% of the time it's be no. Explain your reasoning. Well, there's only so much the board could be. Like that d can be like 200 feet. Like that, the board's only so much. It's only 10 feet long. So the max it could be is probably something under 10. So board is not infinitely long. It's any side effect. Alright, so anytime I'm going to ask you, does this tend to continue indefinitely? Most of the time, the answer to be no. Look at the problem, see what's going on, but most of the time to be no. Let's see if we can do another one real quick. The annual compact disc sales, those are CDs, people. These have CDs. They're modeled by the quadratic function list, where x is the number of years after 1995, and that's annual sales. Graph the function between 0 and 10. So I just typed that in again. I'll do it real quick. So I typed it in. Let's talk about x number. Let's talk about what x and y are, because I kind of skipped that. X is the number of years after. So x is years and f is sales. Okay, let's graph this. See what it looks like. Come on, CD industry. Don't let Tower Records down. And it's taking forever to graph. And I don't see a thing. That's great. Zoom. Let's go zoom fit. See what's up. Come on. Well, that sucks. So that's going good, right? I'm gonna fix my window 0 to 10. It still works. They're just really high up there. If you look at the window, look at your Y. It's going all the way to like to 800. I'm gonna go to 0 so you can see a little better. Let's go 0 to like 800, so you can see the scale a little better. So the cells are all the way up there. That's why I couldn't see anything, because it's all the way up there. Anyway, describe the turning points of the graph. In the same behavior, there's a min, there's a max, that. And it looks like it's going up at the end. Barely, you can kind of see it's going up at the end. Continue the graph for 11 and 12. So let me fix my window. Let's go to 12 now. See if that changes anything. What trend compact disc sales does the graph suggest? That it's gonna go crazy by stocking it. It's gonna increase massively. It's increased massively. Is it reasonable to continue? Again, most times we no. New technology is probably a good reason why. New technology like the iPod or the iPhone is gonna kill the CD star. Anyway, that's a lesson.